So just to kind of recap, we're talking about covalent bonds like to share their electrons in the outer shell that were originally unstable and didn't meet that octet rule. Nonpolar covalent bonds are basically two elements that are equidistant from the edges of the periodic table. And basically what happens is the electrons that are shared, they kind of spend equal time between the two different atoms. So they kind of share their time, like splitting their time between two different houses or two different jobs. So these covalent bonds are said to be nonpolar, meaning that they don't really care whether they're hanging out more with um, let's say if it's methane, the carbon, or the hydrogen, they're kind of equally happy hanging out with both in equal amounts of times. However, the opposite of that is a polar covalent bond. And this is considered to be two elements that are much closer to the edges of the table than they are to one another. And basically here the atoms have an unequal affinity for an electron. One will want to donate or receive with a specific intensity, and the other will want a different intensity to the donation or the receiving. So basically what happens is the electron usually spends more time with one of the atoms than the other. So the bond with the electron spends more time with one versus the other, and so therefore we refer to these as polar. Water is a really great example of this. Water molecule, H2O, which we'll spend more time on next week, is very much so a polar covalent bond. And we have electrons that bond together and hold this electron configuration together, but they like to spend more time with one of the other atoms. So we will see that next week. A third type of bond is very special that we call hydrogen bond. Now, I just talked about water being a polar covalent, but also within water, the bond between different water molecules is what we call a hydrogen bond. So water is a polar molecule, and like I just said, the electrons spend more time with the oxygen than the hydrogen. So when that happens, the hydrogen becomes slightly positive at the edges, and therefore the oxygen becomes slightly negative because again the electrons are hanging out more near the oxygen and less near the hydrogen, and so therefore our protons are playing a role here. But water molecules can actually change. When polar molecules are dissolved in water, so other polar molecules, the hydrogen of the water molecules usually attracts the negative part of the solute, and therefore we have this weak bond. So water molecules are held together. So one water molecule, a second, a third, a fourth, a fifth, are held together by what we call hydrogen bonds. Not this part. This is not a hydrogen bond. That is not a hydrogen bond. That is a covalent polar bond. But when we have one molecule attached to another, which would basically be even a droplet of water, basically those different molecules are held together by hydrogen bonds. Hydrogen bonds are really easily broken. And so that's something that changes. So again, here's our water structure, right? This is a covalent bond, because see how they're sharing. Okay, the oxygen is sharing one with the hydrogen, so therefore this is happy because this only has one ring, so it needs a maximum of two. It's happy, and that's oxygen's happy with this one, but it needs another bond over here to share to make it happy over here. So this is basically what happens is we have these two separate bonds that make up water. Now there's a little bit more negativity and positivity because again the way that this electron likes to hang out. This is a water molecule. This is a water molecule. There's just different ways. This is a pour. This is like a 3D model. If we were in class, we would use these. This is a stick model. But when we have many water molecules, here's one, here's a second, here's a third. This is that covalent bond again. This is that hydrogen bond that's between the actual water molecules. And these water molecules will stick together, but again, they're easily broken depending on what the scenario is. Temperature can easily break these bonds of water molecules to create an excess of heat and then an extreme colds. Again, we're going to talk a lot more in depth about water next week. So each molecule has a specific size and shape. Water, as we just saw, has 2 hydrogen atoms and 1 oxygen. This guy right here is CH4. This is 1 carbon and 4 oxygen. 4 hydrogen. That is methane, which we will see often. So the size is determined by the number of atoms and the size of the atoms, the number of bonds we might have. The shape might be determined by the position of the electrons. So methane, the shape of how molecules recognize each other is really important. And that's really important because of this model. Now, this is example. These are just kind of 3-dimensional models that we kind of like could build together. If you look at this model, and I know we can't turn it around in a 3D way, but basically you can see that it has black, it has white, like a whitish gray, it has blue, and it has red. And if we were to actually pull up the chemical structure and we knew how many carbons and hydrogens and oxygens were in each, they actually would be exactly the same. Now this is endorphins and this is morphine. So let's think about that for a minute. Endorphins are what? Anybody know what an endorphin is? An endorphin is a naturally occurring drug that our body creates, and it creates like kind of highs and lows in our body based on what's happening. Now morphine is not something that our body makes. It is made in a lab, and it is used for things that are helpful, but they can be harmful too. So endorphins kind of can inhibit things and excite things. Morphine usually does some inhibiting of things. It numbs things, kind of inhibits pain and such, which also can trigger other things. Now, if we were to chemically look at the same exact structure of how many carbons, hydrogen, oxygens, etc., these would be exactly the same. However, structurally they look very different, and functionally they do things very differently. One is naturally occurring in the body, and the other one is made in a lab. We can make a lot of things in the lab with the same kind of chemical structure, but sometimes things make them different. When we really look at a lot of man-made things inside of a lab, they aren't always meant for good reasons. Sometimes they're beneficial, sometimes they are not, and that's something to think about. We've been really far in our advances as far as science to be able to make things in the lab very similar to what would have been occurring naturally in nature, but it doesn't always necessarily function the same. Okay, so that's what I want you to think about. And that's the end of our first part of the Chapter 2 chemistry notes.